Welcome back to the lecture series on heat transfer operation. This is Yogesh Lange. In today's video, we will see the individual and the overall heat transfer coefficient, the concept of overall heat transfer coefficient. So, what is the heat transfer coefficient? The heat transfer coefficient, it is the one of the factor that we are measuring whether it is the inside or the outside one, the inside heat transfer coefficient or the outside heat transfer coefficient. Let's consider the hot fluid which is flowing through the circular pipe and the cold fluid is flowing outside the pipe. Now let's see, this is the outer pipe and this is the inner pipe. Now the cold fluid is flowing outside the pipe, that is inner side outside the pipe, and the hot fluid is flowing inside the pipe. Now when the hot fluid is flowing through this pipe and it is separated by this metal wall of the pipe and the cold fluids flowing, what is the in between the surface the space available for it. Now there is an exchange of heat between the hot fluid and cold fluid, and we know that there is a heat transfer takes place if there is a temperature difference. And here also the same thing is formed. The hot fluid give the heat to the cold fluid and cold fluid gain the heat. Now when we have to find what is the overall heat transfer coefficient for this case. Now in this case we will see the HI. HI stands for what? It is inside heat transfer coefficient. And HO, it is what? Outside heat transfer coefficient. And the addition of this inside heat transfer coefficient and outside heat transfer coefficient, it will give the overall heat transfer coefficient. And for this case we will try to find what is the overall heat transfer coefficient. Okay. Now with the help of this schematic diagram we will see what are the number of resistances here and how there is a relation between the inside heat transfer coefficient, outside heat transfer coefficient, and the overall heat transfer coefficient. So this is a metal wall through which the two liquids are separated. At the one side hot fluid is flowing and from the other side cold fluid is flowing. So at the one side of the metal wall a cold fluid is flowing and from the other side of the metal wall the hot fluid is flowing, and there is an exchange of heat between these two. There is an exchange of heat between these two fluids. How? See. Now consider a small thin film on the hot fluid side. Also there is a thin film is formed on the cold fluid side, which we call this is the cold fluid film, and this one we call it is a hot fluid film. Now the heat is transferred from the hot fluid to the cold fluid. Now see how the heat is transferred. Let's consider from the heat is transferred from the hot fluid. So the film surface temperature, consider the T dash. The surface temperature of the metal wall, it is T2. Then it reduces the heat and then now the heat is flow through this metal wall and its temperature is T3, and from that one it is flow through the cold film, and then we call it is T double dash, that is the surface temperature of the cold fluid film, and then it is transferred through the cold fluid. It means the hot fluid first it is transferred near to the surface from the bulk fluid to near the surface, that is called the film. From the film it is given to the metal wall, it is flow through the metal wall, and from the metal wall it is to the again cold fluid film and then to the cold fluid. So this is the heat is transferred from the hot fluid to the cold fluid, and the T1 and T4 are the temperature of hot fluid temperature T1 and cold fluid temperature T4. Consider this is the X1 is the thickness of the cold film and the X2 is the thickness of the hot film, and the metal wall it having the thickness is xw. The thickness of the metal ball is xw. Now this is the structure. Okay, this is the bulk temperature of the fluid, and this is also the bulk temperature of the fluid, of the cold fluid, and this is for the hot fluid. Okay, so this is give the temperature gradient in the force convection. If it is a force convection, this is showing a temperature gradient. Now to calculate, to know the overall heat transfer, overall resistances to heat flow from the hot fluid to the cold fluid. If you see the diagram of this one, then how many resistances are there? The one resistance at the hot fluid, which is we call it is by the convection, means the heat is transferred between the hot fluid, it is by convection to the metal. From the metal wall it is to the conduction because it is a solid material, and from the metal surface to the cold fluid it is by the convection. So from hot fluid to the surface it is by the convection, then conduction, and now here from it is a convection. Okay, so how many resistances are there? So there are three resistances. So what are that? The one resistance by the film of the hot fluid, resistance by the film of the metal wall, and the resistance by the film of the cold fluid. Now first we will see what is the rate of heat transfer through this film is given. Now what we consider the rate of heat transfer through the film, that is the film which is nearer to the metal, and it is by the a convection one, because it is a thin film is formed and the heat transfer between the thin film and the metal wall, it is by a convection one, and we write the equation is Q is equal to HI AI T1 minus T2, where HI is the heat inside heat transfer coefficient, and AI is the inner area of the pipe, and T1 is the temperature of the fluid, bulk fluid, and T2 is the temperature of the surface of metal. So we give the equation number 1. After that one we write the equation, the rate of heat transfer through the metal wall. What is the equation for the metal wall? Now as the heat is transferred through the metal wall, it is by the conduction, so we are writing the equation for the conduction. What is the equation? The Q is equals to the K, conductivity of the metal, AW, area of the metal wall, T2 minus T3, this is the temperature of the surface of the one side of metal wall, and other side it is T3. XW is the thickness of the metal wall. So the rate of heat transfer through this the cold side fluid, we write it is Q is equal to HO AFO T3 minus T4, where HO is heat transfer coefficient outside, AO is the outer area of the pipe, T3 is the temperature of the surface of the metal, and T4 is the temperature of the bulk fluid, that is cold fluid, and the Q is the heat transfer rate. So we write the equation number 1 for the convection in the inside one, then the heat transfer through the metal wall, it is by the conduction, and the heat transfer to the from metal wall to the cold fluid, it is by the convection. So we write all these three equations. Now what we do, we are adding all the three equations 1, 2 and 3. So after addition what we get, so after the addition of this one we will get and write in terms of the temperature gradient, T1 minus T4 is equals to the Q in bracket 1 upon HIAI plus 1 upon KAW by XW plus 1 upon HOAO. Now after solving this one, addition of this, we will get this is T1 minus T4, where Q is the common. Okay, and on that basis we are writing these equations and we get in this form. So we give this equation number 4, where this is the resistance by the convection, resistance by the conduction, and this is the resistance by the convection. So we write, now we write overall heat transfer coefficient. What is the formula for overall heat transfer coefficient? It is Q is equals to the UI AI T1 minus T4. This is the temperature gradient. Q is the heat transfer rate. UI is the overall heat transfer coefficient by consideration of the inside area AI. Or we can write Q is equal to UOAO T1 minus T4, where UO is the overall heat transfer coefficient by consideration of the outer area. Now what we do first, we comparing the equation number 4 and equation number 6 in terms of the temperature gradient. So we are comparing the equation number 6 and equation number 4. So when we are comparing, we can write in terms of the overall heat transfer coefficient, and it is 1 upon Hi is equals to the AO upon AI plus XW by KAW in bracket AO by AI plus 1 upon HO. So we give, this is the equation number 7. So we are taking the overall heat transfer coefficient by consideration of the outer area, and we are writing this equation. If you want to consider the inner area, then you are comparing the equation number 5 and equation number 4. And when you comparing the equation number 4 and 5 and you make it in terms of the temperature gradient, you will get the equation as 1 upon Ui is equals to the 1 upon Hi plus Xw by Kaw in bracket Ai by Ao plus 1 upon Ho in bracket Ai by Ao. Okay, so this 7 equation is gives when you are comparing for the outer area, and here you will get the overall heat transfer coefficient by consideration of the inner area. So that's why it is give UO, and here is the UI. After that, what we say, for the thin wall tubes, inside and outside radii are not much different from each other and is written in terms of Hi and Ho. Now in certain cases, what happens if you comparing the diameter of the pipe and the thickness is very small. So what we do, we are neglecting that part, and because the inside and outside radius is almost the same, so that's why we are neglecting the thickness of it, and we are writing the equation in form of, that is 1 upon UO is equals to the 1 upon Hi plus XW by K 1 upon HO. Means we are, what we do, so because we are considering the radius is almost same, so what we do, we are neglecting this part. We are neglecting this part, and we write in terms of 1 upon Hi Xw by Ka upon 1 upon Ho. So we are writing this equation in this form. Now sometimes what we do, the thickness, if you consider there is a thickness is very small, or the resistance created by the metal wall is very less, in that case we again neglecting this part, and we are writing the equation as 1 upon UO is equals to the 1 upon Hi plus 1 upon Ho, and this is the equation number 10. First case, we are neglecting the radii, almost we consider inside and outside radius are same. Then we are we are neglecting the metal wall resistance because it's very thin, and resistance by created by this wall is very less, and for in that case we are writing formula in this form. Fine. Thank you very much for watching my video. Thank you.